Okay. Okay, so today I'm going to give what I would describe as a grossly underprepared and incomplete talk about some aspects of differential geometry in synthetic scheme world. So we're moving back to stuff that I understand and not stuff that I really don't understand about real schemes and what people actually do. So to begin with, we're going to just start with some stuff from synthetic differential geometry that just carries through straight away. So we're going to do just some normal differentiation, okay? And to do this, we're going to start by talking about some infinitesimals. So we're going to consider the following type. Is this going to set through the spectrums of Rx squared, which is equivalently just the points in R which square to 0. And somehow the fact that we have these infinitesimally close to 0 things in our field are going to allow us to access derivatives. So actually we can see how this works really directly. So given a function f from R to R, we can always compute its derivative. And the way that we do this is by considering another function. So we're going to think g from p to r. So if we want to compute the derivative at x and r, then g of d is going to be x plus p. Okay? And so how do we get the derivative from this? Well, we need to know something about duality here. So a map from D, I'll probably just call this D instead of D1, because we're just about higher ones really. This is the same thing as, well, it's given by a map, by duality, the other way. So it's going to be a map from R. Squared. So this is the same thing as a point in this ring. This map here is determined by a point in Rx mod x squared, which is some polynomial of degree 1. And by duality, it tells us that this map here is actually computed as a polynomial, just applying this polynomial at D. So in particular, it's going to be sort of like A0 plus A1 D. Okay? And checking at 0, applying this at d equals 0, this is the same thing as f of x plus a1 b, and we think of a1 as the derivative of f x. So this is the same thing as f of x plus f dash of x plus d. So somehow this tells us that really close, like infinitesimally close to f of x, we are literally linear in the direction of the derivative. So this may be the intuition that we have about the derivative. And somehow this really actually does work. So like this is not just some theoretical tool, you can use it to calculate derivatives. I mean, so like if I just literally take a function, so r to r given by x squared or something, so just computing x plus d squared equals x squared plus 2x d, where the d squares cancel. This is the derivative. So these things just magically pop out from this. In fact, this sort of thing is true even outside of the algebraic setting. You can do it for analytic functions or smooth functions even. It just all works. So this is some universal way of calculating derivatives, like algebraically. Okay, so we can think of a map more generally. So we can think of a map D to some type F as being a tangent vector. So a tangent vector like this. So we think of it as picking out was it T of 0 in X, and then some line in X that's very close. This is a tangent symbol. So given, okay, now our definition, given T in X, the type tangent vectors is just those functions D. So it's f from D to X, such that f of 0 equals p. And then we can form the whole tangent bundle as well. So this is this collection of all of them, so this is just d times. Okay. So there's a lot more theory that goes on here, but I'm going to use this mostly as motivation for the Étale stuff. Okay. So actually, these things on the face of it don't really look very like tangent spacey apart from the intuition. But we have some facts available to us. So when X is a scheme, we in fact know these are all actually modules. So we get some structure and everything behaves nicely. When it's smooth, they're free. So, okay, these do behave like tangent spaces, more literally. Okay. Let's talk about some geometric intuition for Étale maps then. So Étale maps. So Étale maps come up kind of everywhere in geometry. Like they're in topology already to begin with, or like you have local homeomorphisms. In differential geometry, there are local diffeomorphisms, and now we're going to try and replicate that intuition in scheme land. So, I mean, in differential geometry, which is sort of what we're doing, an Étale map is one which locally is just does nothing to the differential structure of your manifold. So in this world, we can take some point, an open set around it, or we can find an open set around it, so that when we map down by some map F, so X down here, this unrestricted to U is actually a diffeomorphism. So it's diffular. Okay. Now, this game doesn't work so well in scheme world. The reason why is that open sets are just too big, right? I mean, we think of Zariski opens as being like almost everything. So there's no way to express local structure by open sets. However, we do have infinitesimal structure, right? So somehow we are able to talk about really, really close points. And the idea of a local diffeomorphism is that it preserves all these like differential structures, so this local information. So just by repeating the same idea completely infinitesimally, we should get the same idea. So in particular, if I have some infinitesimal information around one of these points, a diffeomorphism should just preserve it. And so we're going to define an Étale map as one which just preserves all sorts of infinitesimal information. Okay, so that leads us to the actual definition. So f from x to y is Étale if so for any FP algebra A and any finitely generated nilpotent ideal in A, then we should have the following lifting condition. So in particular, so if x goes to y like this, and then we've got the spectrum of A like N here, and the map goes this way, spectrum A. So for any square like this, okay, there should be a unique lift of this map here. Okay, so this exists. Okay, why does this say something like lifting infinitesimal information? Well, quotienting by a nilpotent ideal is kind of like removing some infinitesimal, like, some infinitesimal notion from our ring A. And so what this says is that no matter what infinitesimal stuff we remove, it shouldn't matter. I mean, our function should, or we've really grown it maybe. But yeah, so in particular, we've got a special case for this engine. So we can think about the special case. So in this case, if I take spec R, which is just a point, right? And spec Rx mod x squared, and then a square like this. Okay, then this is quotienting by the ideal x in here, which is nilpotent. And so if this map is a tau, then for any square like this, there should be a unique one here. And so what does this say intuitively? Well, for any tangent vector of y in y, any sort of, tangent, and any points lifting of the base point of this tangent vector, there is a tangent vector in X. So in fact, we get an isomorphism of tangent spaces this way. So tau maps, so if F is a tau, then the induced map TPX, T F of the Y is an isomorphism for all P. And this maybe can be read as something like some infinitesimal preservation. In fact, in differential geometry, this is kind of an equivalent condition. Okay. And just as a further addendum to this definition, we're going to say that a type X is how it is a look like. Okay, so the fact that we phrase this as a lifting condition is very, very important to us. And the reason why is that we have incredibly good properties of maps which we sort of define with respect to a lifting condition like this. So exists unique lift against some class of maps. This is like an orthogonal factorization system if you come from category theory world and know what that is. And it always gives us part of a modality. And so this gives us some immediate stability properties that I won't prove, but we'll just say. So, okay, stability. Okay. So, okay, composition of the tau maps to the tau. So, the tau. We are closed, so a tau, now we're thinking about a tau type here, so rather than a tau maps, but the tau types are closed under several typed conformers, so product, sigma, and equality. By products, the index, there's some subtlety here. Products, you can have any index, it doesn't have to be a tau. Here you need a tau index. But, okay, these are really strong closure properties. And very nicely, f from x to y is a tau. So a different way of this for y in y, the fiber does not. Is a tau of type. This is somehow very nice because it tells us that we can reduce to just computing a taunless over points, and we don't need to bother the whole time. Okay, I'm going to make the interesting decision to make my first example a non-example before we actually decide to give a type that is a tau. I'll show you a type that isn't, or a map that isn't a tau. And I'll explain why with maybe some geometric intuition. Okay, so let's consider y squared over y. Okay, so this is some real, like, now we're doing some geometry, so I'm going to draw pictures that maybe help us. This is really just a quadratic in the place. So we have, y equals x is this one here. And this is the projection onto the y coordinate. So why should we expect this not to be a tau? Well, the problem is when y is 0. What happens at y equals 0 is that this equation has a double root, which is something that is bad. It's uncontrolled infinitesimally. But somehow at 1, 0, we have some terrible fuzz that's going on. That we think of it as a bad infinitesimally. So we can see this geometrically that this map is not going to be a tau by this fiber-wise property. So we can just restrict to the fiber over 0. So by doing that, by taking the fiber over 0, you will just, and you can do it, you'll do some tangent product, but you will just reduce to the case where you literally set y equals 0. So this is the same thing spec r x mod x squared also a minus sign, doesn't matter. And now over 1. So this is, we're just asking to reduce, this is Étale. Well, this, if this isn't Étale, then it's definitely Étale. Okay, why can we see this isn't Étale? Well, we can just do it. So, okay, so we're going to go for a contradiction, we want to show it's not Étale. So if it were, then I'd claim the following. So, okay, claim this. This is Étale. We have the following properties for any epsilon in R, epsilon squared is 0, then epsilon 0. Okay. This is maybe an innocent property if you enjoy the law of excluded middle, but we are very incompatible with the law of the excluded middle. The reason why this is bad is by duality. So duality breaks this. The reason why is if we have this, then by duality directly we would see that these two algebras are actually isomorphic, which is or just not, which is actually contradictory. So if we have this, so this is how we're going to prove this result. We're going to deduce that duality is going to break things. Okay, so with this one, we're going to use uniqueness of length to get this fact that our epsilon is going to end up 0. Okay. So, okay, how do we do this? Okay, so let's take some epsilon normal, such that epsilon squared is 0. We consider the following diagram. So epsilon. Okay, maybe I should be clear that I'm actually thinking about the opposite way around. Spec R, and then to go this way, spec R, and then what I had up there is spec R as another x squared. So I'm going to pick a diagram like this. Just picking a diagram like this. So first of all, this information down here is completely irrelevant because there's always a unique map on whatever left I pick is completely, it doesn't matter. So I can just sort of get rid of this and ignore it. And the other thing is that because everything is affine, I can just play the same game in the algebra world, which is nicer in this case. And so I'm looking for a diagram like this, which I can break this. Okay. So this is the quotient map. In particular, I'm going to pick the map which sends x to 0. Okay. So this is x to 0. And that's a great polynomial, so everything's okay. And then I can actually write down two limits here. So I can pick epsilon, or I can pick 0, so I can either send x to epsilon, and then quotienting it gets set to 0, so that commutes. I can send x to 0. Well, both of those satisfies that the x squared is 0 in this thing, and that also gets mapped down. So by uniqueness, implies that epsilon is 0. That's very good. Okay. So, okay, this is a great example of a map that is not Étale. We will fix this at the end, but before I should give us some way to actually tell when types are Étale. So the problem with this definition is, I mean, as lovely and intuitive as it is, it's quite hard to check because there's a lot of finitely presented algebras out there, and there's a lot of nilpoints ideals of those. And so we don't really want to have to deal with checking all of these. So, okay, let me write out what the equivalent conditions are. So the goal is to reduce the number of maps that we have to check against. And I will write out the list, and then I'll explain some terms that I haven't explained. So, okay, it is enough to check against the following classes of maps. So, okay, so is tau. If you remember, it lifts against. Well, to start with, we've just got the actual definition. So sweat A on N, sweat A, where A has C, and nil person. Okay, let's go for number 2. So in this case, this is the terminology that I'll introduce in a second, so don't worry. So we're going to have maps P to 1, where P is closed, dense proposition. So the terminology that I haven't introduced is dense, but we'll get to it. Okay, then number 3, I consider the okay, well, we can extend this fiber-wise to just any closed dense embedding. This is going to be an easy start. Again, I'll mention what the sentence here means. This is the good condition. This is the one which is really easy to check. So we need to just check against maps epsilon equals 0, this is 1, well, epsilon squared is 0, okay, and then finally the sort of extended fiber-wise version of this, so maps, I guess if you write in the spec diagrams, expect A mod A, so spec A, where A is FP, and A squared equals 0. Okay. Let's quickly just introduce this dense notation. So, yeah, I mean, the condition is something which looks very similar to dense, but clearly it behaves somewhat differently to denseness topologically because I'm considering a closed dense thing, and closed sets are normally, right, they can't be because they're closed. The dense is, the closure of a closed set is closed. But the condition that I write down will be reasonable. Actually, I'm going to go with this. Okay, so what does it mean for a type to be dense? So, okay, we'll say A, we'll give this depth. A, so the type is dense for any open open A intersect B is empty, then B. Yeah, that's all correct. Okay, and I guess this makes intuitive sense if you know anything about denseness, that if you're dense, you should intersect with every open set. Somehow you don't miss any part of your space. Okay, and luckily we only really have to think about the proposition case, and this case turns out to be very, very easy to classify. So a little claim that if P is closed with a closed proposition, a closed prop, and P is dense, not okay. And somehow this also makes some sense topologically because this thing is kind of like a closure. If you know anything about that, okay. And luckily this proof is also really easy, so I can do it quickly. So okay. So okay, if let's presume that P is dense, and we want to show that not P holds. Well, P is closed, so not P is open. This is just true in general. And then P intersects not P is clearly empty, and so this is open, and an intersection is empty, so not P must be empty, which is just the same thing as writing not. Okay, lovely. And the other direction, let's presume that we have not P, and we want to show that P is dense. So assume P. Okay, let's pick some open V, some open proposition. So we can think about some types of 1, so everything's okay. And now I'm blanking, but I have it written down, so everything's good. Okay, yeah. So we need to assume that the definition holds, so that P and V is empty, which is the same thing as saying not P and V, but we know not P, not P and V, and some construct some intuitionistic logic will tell you that then we deduce not V. Okay, it's just like pure logic at this point, and which is the same thing as V. Okay, so these are the same things. So we have a great characterization here. Actually, we sort of know what closed propositions look like as well, so we get something even stronger. I mean, closed proposition is just one which is like some element of R setting into 0, so R1 and A is 0. This is what like a closed proposition looks like, and a closed proposition such that not P is where these guys are all not 0. And so this is like these are all infinitesimals. So okay, this statement is going to be like saying that when we prove things about tau types, we can just assume that a finite number of nilpoints are actually 0. Okay, let's give a quick sketch of this thing. It's not too hard, I don't think, but I don't want to write out many details. Okay. So, okay, let's just go through it. I'm probably just going to say it. So 1 plus 2 is just immediate because any closed dense proposition is of this form just by quotienting out by these this ideal that I just gave. And closed dense embedding, this is one way your fibers are of this form. And so we get this for free by fiber-wise preservation for tau maps. Okay, well, this one is also a special case of closed dense embedding because this is a closed dense embedding. I just wrote out what it is. And this is the fiber-wise version of this. So the only thing really to prove is that 5 implies 1. But this you can do by just lining, this is a finitely generated ideal. So what you do is you just line up your quotients sequentially in order, just quotienting these square 0 things, which you can always do. You just pick an order good enough. Okay, so that, maybe I didn't write anything that I consider good. Okay, so with this, maybe we can actually tell when some things are in tau. Okay, so just not for tau, which is maybe not very helpful. So let's give an example of a tau. Let's give an example of a tau and a tau type. Okay. So let's in particular start with, okay, let's start with nice. So example, let G be a mnemonic separable polynomial in one variable. Polynomial. Okay. So what does that mean? I mean, so maybe that G and its derivative are co-prime, but we can just equivalently write that as well, x in R, here that equal to 0 implies G prime of x. So we're excluding the bad things that I have on here, basically. The problem was up here is x had a double root. So we had some of this infinitesimal information that was bad, or not preserved by these maps. And here we're just excluding that case. We're just literally saying, get rid of it. And so by removing this case, somehow we're going to fix everything. So, so then spec Rx mod G for this one. Okay, let's prove this quickly. Okay. So how are we going to do this? Well, we're going to use the nice conditions. So this one is easy to check because there's very few things to check in some sense. So let's let epsilon being r, which is epsilon squared equals 0. And I'm going to play the game backwards in algebra world like we did somewhere before, because we can, everything's going to be affine. Okay, so what we need, so let's say we have a diagram like this. Okay, and we want to first find a list and then show that that list is unique. Okay, finding a list. Well, okay, what does a map like this look like? Well, explicitly, it's a very explicit thing, mapping out of the quotient of a polynomial ring. What we get is, this is just choosing some r in R such that G of R is congruent to 0 mod epsilon, which is the same thing as saying that B epsilon for some B in R. Okay. So now we need to lift this root, which is not really a root, right? It's a root only mod epsilon, so a real root. Okay? And we know what they're going to look like because we know how we quotient down here. So it's going to be something of the form like R plus S epsilon is going to be the lift or something. Okay. So we need to compute this and figure out when it's going to be 0 to do this lift. But my magical talk about derivatives earlier tells us that we know how to compute polynomials when you're adding a square infinitesimal. So this is really something derivative-y. So what we get is that this is G of R plus S epsilon G of R. If someone shout at me if I wrote that wrong. But G of R is B epsilon. Okay, so now we need to somehow mess with this to be 0. And it'd be great if we knew G prime of R was invertible, which maybe this condition doesn't quite look right, but being non-zero is not stable. So this is some magic trick that we're playing. We don't know that G of R is 0, but we do know that not G of R is 0. And we're proving something which is not stable because triple negation is the same as single negation. So by this fact, we deduce that G prime of R is non-zero and is in fact therefore invertible. Again, this is this magic thing about taking negative statements and picking up positive statements and as they do. Okay, so then we can just pick our S correctly. So we use S to be minus B over G prime of R. Then this cancels out by something in B epsilon here and G prime of R there, and so we have a lift. So it's going to be R minus B over G prime of R epsilon for this. Okay, that's step 1. And step 2 is uniqueness, but this is actually also going to be pretty quick. Yeah, okay, let me do it. Okay, so let's suppose we have 2 lifts, so we're going fast. So X and Y. Okay, so what do we know about X and Y? Well, we know that G of X and G of Y are both 0 and that this maps. So what do we get? We're going to get that, well, 0, the same thing as G of X, the same thing as G of X plus 1 minus X. And using some derivative facts, we are going to be able to expand this. So this is G of X. So say the right thing here. Probably G prime Y X minus 1. And why do we know this? Well, this thing is congruent to 0 mod epsilon, and so it's really a square infinitesimal, and so we can do this derivative expansion thing that we were doing before. Actually, pardon? Like this? Does this make sense? G prime of X? Oh, yeah. I've swapped everything in the second half. Okay, there you go. Yeah, but that's not correct. Okay, but this is 0, so this is just g x, y minus x. And finally, we know that g prime of x is non-zero because we assumed that g was separable, and so we can cancel that out. Right. Okay. That is an example, and it makes sense. That's all good. Okay. Okay, there's some other similar examples that I maybe won't accidentally fully for, but we can sort of take a kind of generalization of this thing. So I'll do instead spec. So examples. I take spec Rx mod G. Now I'm not requiring G be separable, but I can fix the situation by localizing some polynomial f so that G prime divides f. Okay, this is the case, and everything is good, and this becomes Étale again. In fact, we can play this same thing. We can expand the number of variables. So I could have written R x1 xn, and then multiply p1 pn, and then instead of localizing one thing, well, we're localizing one thing, but then the Jacobian determinant should divide this thing. So stack of this, such that that P, and by P I mean the collection of all of these things as a map Rn to Rn. This divides. And this is still a power. Again, it's the same proof just applies. You need to do some, maybe some more complicated, well, technically complicated, but literally the same derivative expansions to get this. And then finally, we have maybe some.
If the number of derivatives does not coincide with the number of your relations, then you just invert all minus.
Oh yeah, this would probably work as well. Just about minus. Yeah, I haven't checked this, right? Or is there some dimension?
I don't know. I mean, it looks like a stretch condition, just like the same number.
Oh, no, maybe, well.
Maybe not. No.
I think there's maybe some problems if you don't do that. This is like the same reason why the affine line isn't tau because of the null hypothesis. Yeah, I think maybe that wouldn't work. But.
You risk losing unicity, and I'm not sure what you mean precisely, but if you add
okay, let's give one more example that I think is. Oh, sorry.
Yeah, I see. So if we have no relation at all, then that's as polynomial rings. Then there's no minor to consider. Yeah.
Okay, we do one more example. This is a general one. So okay, A is an FP algebra, and P is an A. Then the localization is going to be a top. So this maps spec A B to spec A. This is a lovely broad class for examples, and the proof of this is not one. Okay, and somehow we have maybe a more general result from this in algebra where you can take arbitrary localizations, but then we maybe lose finitely presented. So we can do it at one point, or finitely many points as well, iterating. Okay, and with that, I think we have the tools to fix our example from before. So I'm going to fix the parabola. Okay, so the idea is that we can just simply remove the bad case algebraically. And so instead of, well, I mean, if we were classical, we could just remove 0, but obviously we can't quite do that. So instead, we can consider spec x, y invert. So localizing at y up here, mod y minus square. Okay, so I literally just removed the case where y equals 0. So we have the parabola, but we just ignore this bit. Okay, And somehow now this is fixed with the projection is Étale. Okay, can we see this using the tools that we've built up? Yes, so I want to check fiber-wise. And so checking fiber-wise amounts to doing some sort of tensor product. So, okay, a fiber of this map, I'll draw upside down because I don't want to do things. So I'm going to write this maybe, what's that, evocatively, to get my point across, that we want to be localizing this, and we're going to think about this. So this is just spec R, but what I mean is that this has a, when we're considering the tensor product, I want the action by R given by the base ring. So because otherwise it's underspecified. So what we have here is something discussed in tensor product, which maybe I'll write down for completeness and then just tell you that you can simplify it. It's like this. So tensor over Ry, and then this other thing. And some simple tensor product algebra tells you that this is going to be equal to the thing in the brackets is going to just be equal to setting Y to R and then also inverting R. It's going to be R localized to R and then X mod. So that's going to be R times X. Okay. So is this always Étale? Well, yes. So I'm going to just quickly. Yes, but with a caveat about characteristic, because we're now doing geometry, so we have to be careful about characteristic. So let me just move a localization to the outside, because that's just going to be quite easier. But I think if characteristic is not 2, then we know that this polynomial is in fact separable always, because R is non-zero. So that's great. Yeah, and that's basically it. So this polynomial is going to be non-separable. Actually, maybe the R doesn't, to be honest. So this is Étale, and the localization is also Étale. So this is finally Étale at the end of our day. And we fixed the whole, or we fixed our polynomial by just moving backwards. Okay, that was all I wanted to say formally about, this is formally Étale. But formally about how things, but I should give maybe some outlook or some places where this can go. So we had some allusions to maybe some connections between this and the Étale topos. Well, this notion is obviously much more general, like we've got loads of things here, and the Étale topos who are just localizing certain maps, certain things which weren't even Étale, but you can fix that. So okay, one of the things that we know is that this is just a fact that we've got proved about local representations of Étale types. They're all locally standard. Okay, yeah. So any Étale type X has a finite cover by pieces of the form that I wrote over here, so to say time by pieces like this, or the form like this. So this is some local description of the Étale maps. Classically, we have one better. So classically, so now outside of our synthetic world, we can actually reduce this even further just to this. So classically, we can reduce to one. Okay, and so what do you mean? So the word is finite cover, finite open cover. So we can find affine sub-schemes of any Étale scheme, scheme has an affine open cover by a finite affine open cover by pieces like this. Does that make sense? Yep. Okay. Classically, we can reduce way further. We can kill all these extra variables, and we can find a finite open cover by pieces of the form Rx mod G 1 over F. And this is really good because this now gets us very, very close to the Étale localization that we were doing before. So before we were localizing, so let me just compare. So for the Étale top marks, we were localizing at spec Rx. Now G, so local. G monadic unverifiable. And actually, we can give an equivalent presentation of this topology. So equivalently, we could ask that Q is spec Rx mod G localized with one of the G prime local again for monadic unverifiable. So this is not too difficult to prove. It involves showing that if you have any if every monic unramifiable polynomial has a root, and in fact every monic unramifiable polynomial has a simple root. There's some induction, I think. I think maybe Thierry did this. Okay, yeah. So this is Thierry's work. And we sort of have then, if we had this local covers thing, we could maybe say that Étale covers are actually covers in the Étale topos, but we're not quite there yet because we don't know how to do this down here at least, and then maybe more stuff down here. But classically this is true. Maybe there's some clever just polynomially argument, maybe some elimination stuff. I don't know how to do this, but this is maybe a nice thing to work on. Okay, and then finally the second point of Étale maps that I can really think of and want to talk about is Galois like covering theory or the Étale fundamental group.
And what was replacing the locality solution by the star?
So if we replaced it by star, then I think everything would be reasonably okay. Well, so yeah, these are all Étale, yeah. But we want to somehow reduce to this case because this is the case that we know from the literature. So we know that these present the Étale topos because this model is strictly in Thalian local rings, which is what they
but so assuming that star is not equivalent to the cross, that, whatever, yes. So in case it's not equivalent,
then we might have to expand. Yes, I agree. This is one of the conditions that Hugo mentioned, that maybe then what we've done outside is not good enough inside. We maybe need to try.
One remark is that I don't know if the algebra in star are flat, so I don't know if it's subcategory.
Yeah, this is actually this is one reason. So we know that all of these are flat. So the fact that this tells us that we can reduce to do like faithfully flat percent something. Actually, it's faithfully flat. But we don't start from here. We don't know how to do it. Starting from here, we just consider this case, which we know. Okay.
But the last we can do the same. I mean, there you had a special case where you don't localize, but it's fine.
Yeah.
There, instead of star, you have only the case where Jacobians.
So I haven't. So what I would need a condition for these to be like unramifiable, but
It's not clear.
yeah. So I don't have to do that. Okay, yeah, just a brief mention then of the other place to maybe go with this quite directly, which is Galois covering theory. So we call map X to Y, and our cover, this is maybe a classic notation, but this is, I guess, in the literature. It's finite at the time, so it's finite, and it's not. To do Galois covering theory, we consider the space of all Galois covers, and then we think of the map from Y to, so if we call this like cov Y, we can think of a map Y to, maybe this is the wrong way to put it, but we want to take each Y in Y and associate to it and an X cover. We want to send this to the list of lists of Y in X. So just pre-image, right, define them. And somehow these things are, I think you consider automorphisms of this. This is like a functor. You consider automorphisms of this functor, so I1, Y. So this is the functor. Classically, this is the automorphism. And this somehow really does correspond to Galois theory. So I think it was speculated this, where we have spec K as Y, then phi1 of spec K is the Galois group, the absolute Galois group. Obviously, this now I'm talking very non-constructively because I've taken an algebraic closure, so it's unclear how much, if any of these results we can expect inside, but certainly there's some analogs of Galois covering. Because nothing I did here was like crazy scary, I don't think. I think we can write down what automorphisms of this thing are, just whether we get any classical results, or because I don't know what an algebraic closure is, right? So,
That's never really built, I think.
so, yeah. So, thank you. Okay, yeah, still that's bad.
Yeah, and I think that at some point we need some profile completion.
I wasn't aware of that, but maybe it's
Well, I mean, in general, the separate but clear as maybe not. I don't.
This is what I'm aware of, but I really
Okay,
haven't
yeah.
got much of this, so I could be completely wrong. Okay, but this, I mean,
Okay, now the previous, okay, it's not, okay, so we put the topology on the automorphisms of the X, and also we also have the topology of the Galois.
yeah.
And then, okay, and then it's safe.
Yeah. Okay. Yeah, I think that's what I have to say.
So what do you mean by finite?
This is the like scheme theory of finite sense. So maybe finite fibers is the thing that is externally.
No, finite fibers is quasi-finite. Finite is the algebraic condition that it's finite generated as a module.
Okay.
So it's like quasi-finite, but without any point missing. So I mean, an open map is Étale, but there we have missing points.
Yeah.
And finite also includes properness.
So do we have a candidate definition?
Yeah.
Yes. Okay. So we can do this. So there's some definition. Okay. Yeah. Okay. I think that's what I would say.
So there was to reduce this case for the. I mean, so there is a question: is it done in Gavin West's paper?
In whose paper?
In his paper, is it what he's doing?
Whose paper? Sorry.
Sorry, Gavin West.
No. So what Wraith does, I think, is just show that the points of the Étale tuplus are strictly Henselian local rings, and then he gives a presentation of the theory of strictly Henselian local rings like this. So he doesn't do any reduction.
But when you justify this, I mean,
Well, because this is literally the theory. So the
yes, it is the theory. But when he says it should be the Étale topos.
Right, so yeah, because they classify the same theory, you get the equivalent topoi, but he doesn't do any like internal reductions or anything. He just says they classify the same theory. So okay. Yeah. Yep.
I have sort of a vague question that I don't properly know how to address, but at some point we talked about the solutions not being unique anymore. If you add more variables.
Okay. Yeah. So there's this difference between. Well, yeah. I mean, there's a difference between smoothness and ramified and Étale, which I didn't really get into, but.
Well, I mean, just take no variables and no relations, and then add one variable, then you have an A1.
Yeah. So this is not. This is not Étale because you can have like two lengths like this. So epsilon, and then the same thing that I did before, so 0 and epsilon. So that we've got more than one solution to the lifting problem.
So this is not to do with something like multiple things that sort of independent infinitesimals. You would have like
No. Okay, then, yes,
So I think you can see this in the argument you gave for, like, you know, you have a the proper polynomial, the first evaluation systems, you use that their derivative has an input pattern that consists.
it's in both. Oh,
Yeah, so that it's subjective or it's linear.
yeah,
And then in the later step, you use that as linear.
because I cancelled. Yeah,
So you need both.
yeah. So if you drop one of these conditions, then you get two different notions, one being smoothness, where you have at least one lift, and one being unramified, where you have at most one lift. And then, I mean, so smooth schemes are obviously of great importance, and now you allow them to multiple lifts, it's no problem.
And do you have a simple example where the situation shows up with a Jacobian, it does two variables, where it's not the.
Well, do you want to just write those polynomials where G divides the Jacobian derivative?
And yeah, I mean, do you have an instance where this shows up in some calculation where you would be stuck if you stick to?
No, I don't know what that is not. Sorry. Yeah.
Okay.
Yeah, I mean, I'm sure I could spend an hour and write something.
Yeah, like when you try it say two different directions, then it's.
Yeah, I don't know. Maybe something like that works, but I haven't sat down and tried to write out an issue.
I did make a comment, I don't remember we said something about this, but I think there's that funny thing going on in this proof that you know, the spectrum of a separable polynomial is the way that like Newton's method, if you start from an approximate root and we get a vector.
Yeah.
Then what's funny is that, I mean, normally Newton's method is an iterative. You get better and better roots. And you don't see this iteration in your proof, but in fact, it comes from the decomposition you had before of a general quotienting by a sequence of quotienting.
Yeah. Okay. Yeah, I didn't know that relation. I mean, this looks like Newton's. Yeah. Okay.
Or it's like hence the setting lifting.
Yeah.
Okay, and so that's the end for today, but we can stay here for as long as we want.